Thanks to the organizers for the opportunity to speak. So today I want to tell you about operations on homology with twisted coefficients. So classically, this story has already been told with constant coefficients by Cohen and Peter May. So before I get into the twisted case, let me say a bit about the classical case in case you don't remember. So these operations are defined on the homology of EN algebras with mod p coefficients. So let X be an EN algebra in spaces. Of course, you can work with other categories, but for today, I'll just talk about spaces. So we have the following operations on its homology. So first of all, we have an operation which I'll write Qi p minus 1. This goes from the qth homology of X with fp coefficients to the pq plus I p minus 1 homology. And we have these operations for all I between 0 and n minus 1. So if n is infinity, then we have these for all I. And we also have some operations which I'll write as Bochstein of these Qi's. So in the case of spaces, these actually are the Bochstein of the previous operations I wrote down. But these can be defined more generally even when the Bochstein isn't defined. So these, of course, land in degree 1 lower. And we usually only talk about these for odd primes. So these operations are usually called the Dyer-Lashof operations. And I'll make a quick comment about the indexing I have written here. I think a lot of people are used to the upper indexing for these. It's just a re-indexing so that the operations raise degree in homology instead of having this multiplication by p. I happen to like the lower indexing, especially for finite n, because when you work with actually constructing the operations, it helps you remember exactly where they come from. But in case you're confused by the indexing, that's why it looks different. Okay, sorry, and we also have these for all I between 0 and n minus 1. We also have an operation, which I'll write as a bracket. So this takes two inputs. So it goes from, say, HQ1 tensor HQ2 to HQ1 plus Q2 plus n minus 1. And this is just for finite n. So this operation is usually called the Browder bracket. Now the last operation I'll mention is a product, which looks just like what you think it would. Okay, so we have all of these operations defined, and it turns out that these operations generate all operations on the homology of X. So Cohen and May showed that these generate all operations, and they also showed that you can give a description of the homology of a free EN algebra in terms of these operations. So they defined some appropriate free functor such that when you apply it to the homology of X, it computes the homology of the free EN algebra on X. So this is, of course, very useful for computations, but it's also just a really nice result in general. So that's all I'll say about the classical case. Now let me start talking about twisted coefficients, which is what I've been working on. So the goal here is to do an analog of their result. So we want to understand the homology of free EN algebras, but with twisted coefficients. So again, we'd like to do an analog of all of their results. We'd like to define these operations and we'd like to define these operations and again give a description of the homology of a free EN algebra in terms of these operations. So if you think about this for a bit, it becomes clear that you can't expect to do this for just any coefficient system. So we need to restrict our attention. So I've chosen to consider coefficient systems that are satisfy the following. So first of all, they should be valued in some field, which I'll call F. It's similar to the classical case where things are usually defined for field coefficients. And I want my systems to also be pulled back from the group completion. So let me just remind you what I mean by that. If you'll recall that if X is an EN algebra in spaces, then we have a group completion map. So this goes from X to, let's call it Y, and this is a map of EN algebras. And here Y is an n-fold loop space. So it's very nice to work with Y because things are nice and abelian here. And so if I have a coefficient system on Y, I can pull it back along this map to obtain a coefficient system on X. And I require that all of my coefficient systems arise in this way. And so coefficient systems like this that are sufficiently compatible with the EN structure are determined by data of a group homomorphism, which I'll call phi, going from the fundamental group of Y to the units of F. And I'll denote this system by F phi. So we'd like to define operations on the homology of X with coefficients in F phi. And I don't really have time to get into that in a 20-minute talk. So let me just say that in an appropriate category, I should of course say what that means, but in an appropriate setting, one can easily define operations as one does in the classical case. So there are no new ideas there once you get the setting right. And once you do this, it turns out that for n greater than 2, you more or less get the same operations as in the classical case. So it's not, I mean, there's a slight subtlety that you get some signs being different, and so there's work to be done to write out the analog of Cohen and May's result for this case, but there aren't really any new ideas, and it really should just be a reformulation of their work. So instead today I want to talk about the case n equals 2 because there things are actually a bit different. So if you remember that classically we had these types of operations, and so we'll start by thinking about what the analogs of those might be in the twisted case. So first I'll say a word about the twisted versions of the Dyer-Lashof operations. So I haven't told you how to construct the operations, but these come from the homology of braid groups. And here that's with a certain twisted coefficient system. And what's really nice about this is that these were already computed by Ellenberg, Tran, and Westerland. So from their computation, I already know what operations I get in this case. And it turns out that this story is similar to in the classical setting. So again, there are some things to write out, but conceptually it's not so different. So I won't talk about it more today. But instead, what I would like to talk about is what happens when you try to define the twisted version of the Browder bracket. So again, the Browder bracket, I guess I just removed it. The Browder bracket was this binary operation that we had in the classical case. So for n equals 2, it raises degree by 1. So in the twisted case, we shouldn't necessarily expect that we'll have this binary bracket defined. So instead of looking for a binary operation, we're instead going to look for an n-ary operation for some n. And these n-ary operations should look like the following. So here, when I'm writing homology of x, I have an extra index going on here. I'll say what that is in just a second. So these operations take in m inputs in the homology of x, and they land in the, well, with the a indices, you sum up all the a's. With the n indices, you sum up all the n's, and you add, sorry, it's a bit hard to see, you add m minus 1. So first, let me say what these a things are. So this is just an extra indexing that refers to the component of x that we're working in. So here, ai is in pi 0 of x. So this is a thing you can easily keep track of classically, but it's not really necessary for the operations. But in the twisted case, it actually makes a difference which component we're in, and so we have to keep track of it here. And I also want to make a comment about why I'm looking at operations in these degrees. So if the Browder bracket were defined, and I were to iterate it m minus 1 times to end up with an operation that takes in m different inputs, then it would look exactly like this. So that's why I'm looking at operations that look like this. And these operations come from the m minus 1 homology of the braid group on m strands with coefficients and a certain representation that I won't describe because it's induced by representation of the pure braid group. So instead, we'll consider the homology of the pure braid group with coefficients in f. And I need to tell you what the action of the pure braid group is on f in this case. So let me just write down generators for the pure braid group. I'll call them alpha ij. So here I take the jth strand and I wrap it around the ith strand, but do it behind all of the strands in between. And here we always have that I is less than j, and they range between 1 and m. So if you take all of these, they generate the pure braid group. And here alpha ij acts on f by multiplication by a unit that I'll call qij. And I won't write down explicitly what that is here, but I do have a very explicit description for what this is. And its formula is determined by the data of, well, first of all, ai and aj. So these are the components of x that the ith and jth inputs are in. Also the data of phi, which was this homomorphism that determines our coefficient system, and by something else that I don't have time to define, but that I'll call c. So this is some function that comes from the E2 structure on y. So some function you can write out, and given this data, I can write down the formula for qij. So once I have all of these units, that determines the action of the pure braid group on f, and that's what I mean when I write this homology. So we want to figure out what this homology is. And with constant coefficients, this has of course already been computed. So computations of, for instance, Fred Cohen and Arnold, perhaps others have also done this. These computations imply that if all of the qij's are equal to 1, so we have constant coefficients, then the dimension as an F vector space of this homology is equal to m minus 1 factorial. So that means that in this case, we have m minus 1 factorial linearly independent operations. And it turns out that these operations all come from iterated Browder brackets. So here we have constant coefficients, so the Browder bracket is defined, and there are m minus 1 factorial linearly independent ways to iterate it. Okay, but that is the constant coefficients case. What about with twisted coefficients? So I've done some computations that allow me to say something about what this is depending on what your units are, the units determining this action. So for instance, I can say the following. First of all, if we consider the product of all of the units, so the product over all I less than j, this product is not equal to 1 if and only if this pure braid group homology is equal to 0. So in this case, there just aren't any operations. I can also say that if this product is equal to 1, so that we do get something non-zero, and we make the further assumption that the product of all of the subproducts are not equal to 1. So what I mean by subproducts are, I take all I less than j contained in some index set I, where I ranges over all proper subsets of 1 to m. So if I assume that all of these subproducts are not equal to 1, then I get that the dimension as an F vector space of this pure braid group homology is equal to m minus 2 factorial. So in particular, in this second case, which I'll just comment, there are examples where this actually arises, we get m minus 2 factorial linearly independent operations. And what's noteworthy about these operations is that they don't decompose into operations of lower arity. This is a bit surprising, actually. Lower arity. So why we know that they don't decompose is because if we tried to define an operation that used only a subset of the inputs, we would need one of these subproducts to equal 1 in order to get something non-zero by the first part. So because of this assumption, we know that our operations don't decompose. So in particular, this means that we don't have the usual Browder bracket. But what we do have is some strange m-ary version of this bracket. This is a bit surprising. I sort of assumed at the beginning that this bracket would sometimes not be defined, or maybe be 0, and would other times be defined like usual. But it turns out that in some cases you get an m-ary bracket where m is greater than 2, and you don't have a binary bracket. So this is just an illustration that in this case, the Browder bracket story can be much different from the classical case. So maybe I'll end by summarizing what I expect the result to be in the end. So this is still work in progress, but I conjecture that all of the operations will be generated by the twisted versions of the Dyer-Lashof operations, these twisted Browder brackets that don't decompose, and a product, which I haven't talked about today, but depending on your philosophy, it's either partially defined or it's often equal to 0. But one can define a product. And so I expect that all of these operations will generate all operations, and then I should be able to give a description of the homology of a free E2 algebra in terms of these operations, just like in the classical case. So thanks for listening.